Hello?
Oh, sorry, I was with the microphone muted. But we would like to express our gratitude to Tomás for presenting his work here in our AI Math conference. And Tomás, you have about 30 minutes. Okay? Thank you very much.
Okay, perfect. So I will start. So thank you very much for the organizers for accepting me for this really nice event. I'm Tomás Silva from a PhD student from the University of Campinas in Brazil. And I will talk a little bit about machine learning Sasakian and G2 topology on contact Calabi-Yau 7 manifolds. This is actually a joint work with Dattavia Agrawal, Yang Hui He, Eli Hayes, Ed Hurst, and Henrique Saerpi. And basically, I will try to summarize a paper that recently appeared. I realized that during this event that the main background of the participants are in arithmetics and number theory. So I will try to make these terms in the title a little bit more precise. So this is the agenda of today's lecture, but let me start to saying little things. If you're not so familiar with Calabi-Yau manifolds, basically they are Kähler manifolds with trivial canonical bundle. So that's what I understand of Calabi-Yau manifolds, Kähler manifolds with trivial canonical bundle, or rich flat manifolds. They are, in some sense, equivalent definitions. And why we are interested in Calabi-Yau manifolds? So basically, we have this thing in theoretical physics called string theory that says that the universe is composed by 10 dimensions. So you have like 4 dimensions proposed by Einstein's general relativity, that the 3 spatial dimensions plus the time. And we have another 6 hidden dimensions that are in some sense compactified into what we call a Calabi-Yau manifold. So Calabi-Yau manifolds are 3 complex dimension manifolds. That means 6 real dimension manifolds, and they somehow encode the actual dimensions. And in this talk, we will be interested in 7-dimension manifolds called G2 manifolds that arises as from a very similar problem. So we have this theory called M theory that basically stands string theory, but instead of describing the observable universe in 10 dimensions, it describes it in 11. So we need a 7-dimension compactification. Okay, basically the construction I'm interested in is of a Calabi-Yau threefolds in weighted projective 4 spaces. So the first step to do this construction is doing the classical identification of 5 points in C5 with the weighted line in P4. So we have this weight vector. It's an integer vector of what we call weights. And we identified points in C5 with the weighted line in P4. The next step is to restrict those lines to the anticanonical divisor hypersurfaces, and then we get 7,555 weight vectors that indeed produce a Calabi-Yau threefolds. We will see later on a precise condition for the weights to produce Calabi-Yau manifolds. If you're not that familiar with this construction, you can imagine it as a very well-defined combinatorial problem, and that's why we get some nice numbers like this. So I'll be interested. I'm sorry. Oh, okay. So I'll be interested in the Calabi-Yau links. What is a Calabi-Yau link? So given a weighted homogeneous polynomial with a fixed degree d associated to a weight vector, we'll be interested in the intersection of the zero locals of this polynomial with a very small sphere around the orange. So basically what Milnor did in 1969 was to prove that the so-called link of the singularity, that is intersection, is compact and is smooth 2n+1 dimensional manifold. That's what is called the weighted link of the singularity. So in this figure here on the right, basically we have the intuition behind it. So we have this curve, let's say, that's these polynomials, right? The zero logs of the polynomials with an isolated singularity at the origin. We are intersecting with a sphere, and we get the link associated. And as I told you, we have a very precise combinatorial condition on the link to it attends the Calabi-Yau condition, that is to have a canonical bundle trivial. So this combinatorial condition is that the degree must be the sum of the weights. So just remembering, only for 5,555 weight vectors, we can achieve this combinatorial condition and indeed build Calabi-Yau links. Okay. So what is interesting about those links? So basically we can define what is called a contact form on the link. If you're not familiar with contact geometry, you can think about it as a sibling of symplectic geometry in odd dimensional polynomials. So as we will see later, we are dealing with 7-dimensional polynomial manifolds. I'm sorry, with 7-dimensional manifolds, and basically when you do the circle fibration over the link, we can construct this contact form. This is one form, and in turns the contact form will give a hub vector of a characteristic one foliation in the transverse scalar structure. And once we have constructed this angular contact form, we can produce a calibration on the link. This is the so-called G2 co-calibrated structure. That is basically a tree form. So here we are constructing this by wedging with the Kähler form. So we have this one contact form wedged with the two Kähler form that produce a tree form. That is the so-called G2 structure on the manifold. And just a note, here we consider threefolds, right? So the link will be 7-dimensional. Well, what is interesting about it? We can define a bunch of topological invariants of the link that will be interesting to the underlying G2 and Sasakian structures. And the first one I want to talk about is the Sasakian Hodge number. So basically, we are defining the dimensions of the cohomology spaces of some very clever spaces, right? So some papers prove it, that from cohomology spaces satisfying P plus Q equals 3, the Hodge numbers of the link is equal to the complex dimension of some associated Milnor algebra. This Milnor algebra is simply the quotient of the total space by the Jacobian of the underlying polynomial that defines the link. So we have a way to actually compute numerical values for these Sasakian Hodge numbers. Yeah. So basically, in this work, a first step was to actually implement this theorem, and we computed for all the 7,555 Calabi-Yau threefolds that produce 7-dimension links. We actually computed all the H30 and H21s. And this graphic right here on the right, it represents the distribution of those invariants. And another type of invariance that we focus on this work was the Crowley-Nordstrom invariance. That's a homotopy invariant that is basically an extension of the Euler characteristic and the signature of the polynomials. So I really don't want to talk that much about the spin structure and other stuff like this, but this naively can be seen as other topological invariant for this type of manifolds. And here again we have the distribution of those invariants from all over the data set of 7,555 polynomials. And for last, as a side product of those two previous computations, we have the length of the associated Grobner bases. So in order to compute the Milnor algebra and the Crowley-Nordstrom invariants, we needed to compute the Grobner bases of the associated polynomials. It was a very expensive computation that took a lot of months. If I remember correctly, was something of the order of 3 months to compute the Grobner bases of all those polynomials. And as we will see, we did some machine learning experiments in order to predict the length of the associated Grobner bases. Here you can see the distribution of the length of the Grobner bases for the all data sets of polynomials. So let's talk about some machine learning. So basically, as I said, the link singularities, the Calabi-Yau links are defined by a polynomial and a weight vector, right? So basically, our idea in this work was to not considering only the weights associated to the links, and see how much information you can retrieve by only considering the ambient space. So here is the schematic of the type of experiment we did. So we fed a convolutional neural network with the weights associated to each Calabi-Yau link, and try to predict one of the what we call learnable data. That is the Sasakian Hodge numbers, the Crowley-Nordstrom invariants, and the Grobner base length. And that is, I mean, computationally, that is a very classical approach. Our neural network is very small sized, 32 by 64 by 32, and with very canonical, let's say, optimizers and cross-validation procedure. And well, for the Sasakian two ones, we obtain a very high accuracy. These R squared measured right here basically means um, the variance of the observed data against the real data. So it's a number that varies from 0 to 1, and as closest to 1 it gets, the better the regressor is performing. And here we have the mean absolute error that is in the order of 5% of considering the maximum that these numbers achieves. And again, for the Grosvenor basis length, we also obtained a very good accuracy, let's say so, with 5% error margin. And this, let's just a quick comment, that was not true for the Crowley-Nostro invariant. So the Crowley-Nostro invariant, we didn't achieve good results. So it was indistinguishable for actual learning and a random choice of numbers between this distribution. So we may focus on the good results we obtained on the Sasakian H21 and the Grosvenor basis length. So these good results, they motivated the proposition of two conjectures. Let me first talk about conjecture 3.2. So as I said, this work was the first one to actually compute the numerical values for the threefolds, the Sasakian Hodge numbers for those threefolds. And when we plotted the Calabi-Yau Sasakian Hodge numbers against the Calabi-Yau Hodge numbers, we observed that the Sasakian Hodge number was always less than or equal to the Calabi-Yau Hodge numbers. And this was, let's say, is in some sense empirical conjecture. The first conjecture is a little bit more interesting because, as I said at the beginning, we have two, let's say, defining features of the links. We have the weight vector and we have the polynomial. And we achieved these very good predictions only using the weights. This is, we didn't use the polynomial for the predictions. We did use the polynomials for actually computing the Hodge numbers, but for the machine learning prediction, they were not used. So this was very strange for us because, in some sense, the ambient spaces knows the topology of the link that can arise in it. And this conjecture basically says that the polynomials aren't important for the Hodge numbers. All you need to know is the weights, and the weights carry all the topological information in this sense. We call it the weak R equivalences. And another step we made was to do a symbolic regression on the data, since the weights are the seems to be the only important information carrier. We tried to do a symbolic regression to predict rational polynomial on the weights that can give you the Sasakian Hodge numbers, and yeah, that's the output. I mean, it may see a little bit ugly, these coefficients, but it's way better to attribute values to W0 to W4 than letting a supercomputer run the experiment for months. So this is a way more simple expression to compute than this one. And as you can see, in this plot, we have basically the predicted, the symbolic predicted formula against the actual values that was computed using the Milnor algebra. And you see that we have an almost an identity relation, right? So the performances here were also really high. And this in some sense, inspire us to seek for a formula that describes the topology only using the weights. So let me finish it saying that doing some recapitulation of what I say. So basically, in this work, we generated the largest Calabi-Yau linked database. So we computed for all the 7,555 polynomials we computed in its topological invariance. We observed that the neural networks could predict with very high accuracy the Sasakian Hodge numbers, and we made some conjectures, basically that the ambient spaces knows all the topology that can be built inside it, and that the Sasakian Hodge numbers are less than or equal to the Calabi-Yau Hodge numbers. The next steps are to prove those conjectures, of course. We were also trying to extend the computations for another Hodge numbers, let's say for Calabi-Yau 4 folds, 5 folds, etc. And we are looking to analyze other Grosvenor basis dependent quantities. Since the Grosvenor basis appears to be a very machine learnable, let's say, feature of those polynomials, we are trying to determine other geometric aspects dependent on the Grosvenor basis. So that was what I prepared for today. Here's the archive link for the work. That's some reference. I use it, and that's all. Thank you very much.
Hi, Tomás. Thank you very much for your presentation. I think we have some questions on the chat. Can you see?
Yeah, so
Sajad made some questions.
So let me read the first one. Vectors of input. Yeah, they were computed in some previous work. Let me show you an example. It's as I mentioned, it's a very combinatorial problem. So that's a way to deal with this construction. Here in the paper, we have some examples of it. So, for instance, are you seeing my screen, right? Are you still seeing my screen? Yeah. So basically, for this weight set, which gives you a degree of 225, we have monomial bases in these 7 terms. And basically, what it did to produce the polynomials was initialize the completed space of polynomials and try to kill those that not satisfies homogeneity conditions. So that's I don't know if it was clear to you, Mr. Sajat, but which software did you use it for the calculations? So use it SageMath and Python to the computations. And please share with you. Okay, I will send you the slides by email.
Any more questions? Any more questions? Okay. So I would like, on behalf of our organization committee, we would like to express our gratitude to Tomás for his presentation. And so we will be online again on 2 p.m. Okay? Thank you very much.